Welcome to the video for slope fields day 2. In this video we're going to take a look at a couple of examples of matching slope fields to their differential equations and some properties of differential equations, as well as how this might show up on the AP test. Alright, to start us off we have 6 slope fields here and 6 equations, differential equations, and we want to match the slope field to the differential equation. I'm going to leave this to you as a warm-up, so I want you to find the matching slope field to the differential equation and be able to give a supporting reason as to why you made that match. So go ahead and pause the video here and take a shot at trying to match these 6 slope fields. Alright, so I matched graph A with function 4, and the reason I did that is I noticed that there was 0 slopes anytime x was 0, and that would be the case with function 4, or differential equation 4. Graph B I matched with equation 3, and that's because I saw the 0 slopes when y was 2. Graph C I matched with differential equation 2, and that's because I saw what appeared to be 0 slopes when x was 0 and undefined slopes when y was 0. Graph D I saw the periodic behavior, so I matched it with a periodic function. Graph E I matched with option 5. I noticed a slope of 0 anytime x was equal to y. So that's when x is equal to y. Oops, m equals 0 when x equals y. And then finally, graph F I matched with 1, and the reason for that is when x was 0, I saw that e to the x was equal to 1, and it looks like we have a slope of 1 there. Alright, try to do the same thing again with example 2. We're going to match, and these are good problems here, so take a shot at matching them. Go and pause it now. Alright, so what I oftentimes will do is take a look at the equation and see if I can find where 0 slopes occur. And with this equation we get a 0 slope when x is 2, and that happens on graph B, so that's the match I would make. On the second one I'm getting a 0 slope when y is 0, and that happens only on graph D, so I match this one with D. The third one, there's 0 slope at x equals 0 and an undefined slope at y equals 0, and that's going to occur, we've got the undefined slope when y is 0 and the 0 slope when x is 0. So I matched this one with C. And finally the last one, this x plus y, tells me I have a 0 slope when y equals negative x. So along the line y equals negative x, I see 0 slopes there. Okay, example 3, this is an equation or a question that was found from a AP test. It says the slope field of the differential equation will have vertical segments, and we want to know when. So remember that vertical segments are when we get some number divided by 0. So if we want to set our denominator equal to 0, that will tell us where a vertical segment exists. And solving this out, we get negative 2y is equal to 4x, or y is equal to negative 2x. So anytime y is negative 2x, we should get a vertical segment. It would be safe to plug this into the numerator to make sure that that doesn't cause a 0 in the numerator, and we try it out and we get x squared times negative 2x plus negative 2x squared. And that doesn't simplify down to anything that's equal to 0, so we're good. Alright, here's another AP style question where they give you a slope field and they ask you some questions and determine whether they're true. And this first question says, which one of these 3 statements is true? And it may be more than one. So when y of 0 is greater than 0, so when our initial condition is greater than 0, so maybe our initial condition is here or here, does the limit as x goes to infinity roughly equals 0. Well, if we draw in the curves which satisfies those initial conditions, you get something that looks like that, roughly. And we can see that as we go out to positive infinity, our function grows without bound. So this first statement is false. In the second statement, they say let the initial condition be between -2 and 0. So we'll just plot some initial condition between -2 and 0. And if we were to draw in and go with the flow roughly what that looks like, we would see that it's kind of pinned between those two horizontal lines. And as we go out to infinity, do we approach -2? And in fact we do, because this horizontal line is at -2. So the second statement is true. And then finally, in the last case, if our initial condition is less than -2, so maybe our initial condition is down here, which means our particular solution might look something like that. The limit as x goes to infinity is approximately 0. And again, it looks like we're approaching -2 as we go out to infinity. So option 3 is false. And so we are left with only 2 being true. And fortunately for us, that's one of the available answers. Only 2 is true. Remember, as a time-saving AP tip, one of the things you can do when you're going through this is once you've established that 1 is false, you can rule out version A and version E as possible answers. And then when you learn that 2 is true, you can rule out version C. And at that point, you have a 50-50 shot. If you didn't know how to test the third point, at least you've narrowed down your options to more reasonable answers. All right, let's look at example 5 here. This is a good, complex, multi-layered free response type question that you would see. Okay, so we have a differential equation here, xy over 2, and we're supposed to graph the slope field. So go ahead and pause the video and take a shot at graphing it yourself, and then check back. So pause now. Okay, so I've drawn the 0 slopes in black, and ignore that blue line there, but the 0 slopes in black, and then the red lines are the +1 or -1 slopes, and then the blue lines are the ones that are relatively between 0 and 1 or greater than 1. Okay, there's our slope field. Part B says let f be the function that satisfies the given differential equation. So we can consider kind of like f is our y as we solve this out. Write an equation for the line tangent to the curve y equals f of x that passes through 1.1. So this is just a review of linearization. They're wanting us to write a tangent line. So our tangent line is equal to where we're tangent from. And so f of 1 plus the slope at 1, 1, which would be 1/2 times x minus 1. So quick review, this was y1 and x1, and this was our slope at y1, x1, or x1, y1. Then use your tangent line to estimate the value of f of 1.2. So what we have here is linearization. F of x, or more specifically, let's do f of 1.2 is approximately equal to L of 1.2, and L of 1.2 is 1 plus a half times 1.2 minus 1. And we find that f of 1.2 is approximately equal to 1.1. Okay. Part C, find the particular solution to the differential equation. So it looks like we're being asked to do separation of variables to find the particular solution. So 1 over y dy is equal to x over 2 dx. So I've separated my variables and now I'm integrating them. I get natural log of the absolute value of y is equal to x squared over 4 plus c. If I go about solving this equation for y, I wind up getting y is equal to some unknown value e to the x squared over 4. At this point, we can find that unknown value of a by plugging in the initial conditions, and we wind up finding out that a is equal to e to the negative 1/4, or you could say 1 over e to the 1/4 is equal to a. So now that we have our a, we can actually write the particular solution. The particular solution to this differential equation is y is equal to e to the negative 1/4 times e to the x squared over 4. And they want us to use this to evaluate f of 1.2. So we can stick 1.2 into this equation, and we find that f of 1.2 is equal to, if we stick 1.2 into this, we get approximately 1.1162. All right, finally in part D, they ask us some questions. They say, compare your estimate of the function found in part B to the actual value found in part C. So our linearization came up with 1.1 as an estimate, and our separation of variables gave the exact value, or our rounded decimal, of 1.1162. And it looks like our actual value was slightly higher than our estimate. So our estimate was an underestimate. And the reason for that has to do with something that we learned in linearization, and that has to do with concavity. Since our function is concave up in the first quadrant, the tangent lines will be underestimates. Will be below the function. So, and the reason that I knew that it was concave up in the first quadrant is you can see that as we move to the right, our slope is increasing. As we move up, our slope is increasing. As we move diagonally upwards and to the right, our slope is increasing. So our function has a second derivative that's positive. We could have found the second derivative if we wanted to go that route and prove that it's positive everywhere in the second quadrant. But the graph kind of shows that the curve at that point, 1, 1, would be concave up. Alright, so this video kind of served as a exploration of how slope fields get assessed in the AP test, and we'll have one more day working on slope fields. In that day we're just going to practice some more of these AP style questions before we move on to the next topic. So thanks for watching. Have a good evening.